Hello, friends. This is not what we expected, is it? So, we're going to try and do the lecture piece today, and then I want you to use items you find around the house to build a model of it, just like you would have in class. So, what we're going to talk about today is the proton chain, which I think we discussed briefly in your questions, and I believe I left my dry erase markers in the kitchen. Hold on. I did leave the markers in the kitchen, and more importantly, I left my coffee there too. This could have been bad for all of us. All right, so here we go. Start. What I'd like you to do is take notes down about this, of course. Pull the old whiteboard in a little closer, see if I can zoom in on it. I'm still trying to figure out how all this works. Which way do we go? Which way do we go? Okay, there we go. Let's start here. So, of course, label your diagram, always. Proton. Proton. Chain. I mean, this is critical for understanding how the sun... Ooh, that's really small, isn't it? This is quite the interesting game, friends. You're very patient to do this today. I hope this helps. So, this is really crucial in understanding how the sun operates. This is literally at the core of what the sun does. And it's how the energy that powers the whole solar system operates. This is where it all begins. This is why it's crucial that we understand it. It's called the proton-proton chain because it takes place in two sets of chains. So start by drawing in your first set of protons. You have two up here. Can you see those okay? Yeah, that's not bad. And two down here. Yes? Label these, of course. You got to label things as H1, each of them. Can you see this okay? Is it reading all right? Yeah, maybe a little hard to read. Let's start over here. Let's see if I can make it a little more clear. Maybe tilt the screen this way. Yeah. Okay. I'm trying, guys. I'm trying. So yeah, these are all single hydrogen protons. Remember, hydrogen only has one proton in its most basic form. And because we're talking about the core here, and it's at 15 million Kelvin, it's so hot that this is all in a plasma state. There are no electrons directly connected to any one single proton. So then what happens is that these two protons, separately from these two, but they're going to go through the same process, collide. And in this collision, that's right, blammo, because you got to use a powerful word when you think about nuclear fusion. You got to use a word that really exemplifies the power, just the immense power produced at this point. And blammo, well, blammo is personally as close as I can get. So blammo. Blammo. So much energy is produced at this point. Not from that directly, believe it or not. This releases this funny little particle. Well, a couple funny little particles. The first one is called a positron. All right. Now, the positron, and you might just write this down, is an anti-electron. That's why it's got the little plus symbol. You know how electrons are like this with the E, lowercase e, with a negative symbol? This is a lowercase e with a positive symbol. It's a positron instead of an electron. It's an electron particle. Well, a quantum particle. My apologies. It's a quantum particle. And these two collide and immediately destroy each other, annihilate each other. And they produce, in the process, two gamma rays. Let's make those green. Let's make our gamma rays green. So they produce gamma rays, two of them. Ooh, I don't know if that's going to work. Can you see that okay? Oh, not really. Shucky darns. Get a different green. That's so much not better, is it? Maybe it's a little better. Maybe I'll just go ahead and draw those over in black. Yeah, these produce two gamma rays. Now, this may be hard to read, and I understand that. I will go back and possibly look at other diagrams to help you do this. But this is everything I'm going to ask you to produce in your model. So here's a gamma ray, and here's a gamma ray. Now, this first set of processes takes a long time. It takes about 1 billion years. Now, and that's if we're following one single set of protons. If we're looking at the whole process all at once in the core, this goes on billions of times a second, if not more. I can't even remember the number off the top of my head. It's like times 10 to the 34th or something crazy. It's happening all the time because they're so dense. Like the density, and I should have that number in front of me, and I don't, but I could. Wait, the book's right here. I know it. I just saw it. There it is. Hold on, friends. Everybody keeps an astronomy book on their footstool, right? Let's just look and see, shall we? Doobity-boo. Why is the sky blue? That's not right. The heart of the sun. Here we are. Solar energy production. I just want to give you that core value number. Do you guys remember the density of the core? Any of you? What? I'm sorry. I can't hear you. Hey, I did actually remember it. That's creepy. It's 150,000 kilograms per cubic meter. That's unreal. But that's the density it takes for this process to happen in order to overcome that strong nuclear force. All right, let's get back to our diagram. Are you excited? Okay, I'm going to try and hurry this along now. My bad. This does form. Oh, and it also releases, before I forget, a neutrino. Now, there are billions of neutrinos passing through your body right now. They're crazy small little particles that are massless, basically. And yeah, they're weird. They're one of those things that's really hard to detect, but tell us quite a bit about solar behavior in the long run. We can get into that some other time. So what we produce now is a strange form of hydrogen called deuterium. So we have a proton. And a neutron. markers so squeaky? So now we have a proton. Let's go back and maybe label these protons, yes? More of these is going to take too long. So here's a proton, 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 neutron, neutron, proton. We got protons over here. That's a proton, proton chain. Get it? Ta-da! This is what is called deuterium, or H2. Now, what happens next happens quick. Another free-floating proton collides one of our little H1s. These collide. And blammo, we have another nuclear reaction that occurs. Remember, nuclear fusion is the fusion of smaller nuclei into larger, heavier nuclei. So here, we're going to go from, okay, let's label this again. There's another H1. That's what I'm saying. This diagram is complicated. But I want you to understand it. It's crucial to our understanding of how stars operate and where energy comes from in the solar system. And this creates a gamma ray, yet again. Remember, gamma rays have the highest frequency of any light wave and can do the most damage. They're the most powerful. And that's all we're creating in the core is gamma rays. Then this forms a whole new atom because now we have two protons in each atom. And one neutron. This creates a more stable nuclei called helium-3. Now, this is an unusual form of helium. It's kind of rare, but it does occur. H3, all right? Then, so this process here in the middle takes about 1 second. So we go from a billion years to a second. And now, over the course of the next million years, if we're following a single proton through this process, it'll take it that long. But again, the density is so high that it happens all the time. These collide. And we produce H4, 2 protons, and 2 neutrons. But you notice there are 4 protons here. So it actually releases, well here, let's label this again. Make sure you're labeling everything. This is helium-4. And this releases in process, well, what's got to be released? Bingo, that's right. 2 protons. Or, once again, we're back to our original H1s. And these can pop back over here and start over. So this process continues until we deplete enough of the hydrogen and make enough He4 or helium-4 that the process can't repeat. So I hope this helps. Understand it. And again, I want you to make a model of this. I'm going to type up some instructions for you next and post those with this video. So let me know how this goes. Good luck. And thanks for your patience.